And next, we're going to move on to the section where we talk about dielectrics. Dielectrics we can use to change the capacitance of a capacitor by inserting a material that is an insulator between the two conductors in order to modify the electric field. So as we place more and more charge on the capacitor, we'll eventually get to what's called the breakdown voltage, where you'll be able to zap the electricity through the air. We're going to talk a little bit more about that in a second, but what the dielectric does is it basically adds a multiplier. So we talked about this base capacitance, which is why there was a naught on there. That assumes that basically there's air, but the full formula is really the capacitance is equal to this dielectric constant times E naught A over D. I'm not sure why they don't include the K from the get-go, but that's the way it's done in every book I've looked at. So this K value is the dielectric constant. So what does a dielectric do? A dielectric is a material that we put inside a capacitor to basically shield some of the charge. These materials are typically made of plastic, and in which case they have molecules that can be oriented. So we have positive charge and negative charge, and those charges orient with the electric field. The presence of these extra charges in the dielectric reduces some of the negative charge on the metal. So it kind of acts as a shield. So we have just as much voltage across the capacitor, but we don't have as much risk of shock. So this allows more negative charge to be placed on the volt for any given applied voltage, and therefore the capacitance increases. So here's some dielectric constants, but what we're trying to avoid is this breakdown voltage. Every material has a voltage that if you put enough of an electric field across that material, it will turn into an inductor. It will allow a shock to pass. And so this is what happens when you touch a doorknob in the winter, is you've reached such a voltage that such an electric field that you've reached the breakdown voltage of the air. And this is called a Weimhurst machine, where we crank it and create static electricity. Every once in a while you see a little lightning bolt flash across as it reaches the breakdown voltage for the air. And we can use these to create cool artwork. Like this thing, where basically I used a capacitor to create a potential difference across this material, and here we can see the breakdown of the material as the lightning bolt breaks off and forms these fun patterns. So the dielectric constant of a vacuum is defined as 1. Air is slightly more than that, but we can get to very, very good materials for dielectric constant. And so here, probably the best material for capacitor is this one, because it has a high dielectric strength. It can handle a very, very strong electric field and has a very good dielectric constant. So this dielectric strength is the volts per meter. So this we can use in our volts equation. Volts is equal to E times D. Says here we see a voltage and a distance, and that's how we're going to figure out what voltage we can put on, because this is basically the electric field. So this is telling us how strong of an electric field it can handle before it starts to break down and turns into a conductor and allows those charges to pass. So now we're going to look at that all mathematically. And so here we have a capacitor is made from 2 sheets of aluminum foil separated by wax paper. Apply the simplest capacitor you can form. The sheets of aluminum foil are given this. This is going to give us our area. And the thickness of the wax paper is this, and we know the dielectric constant, and we know what its breakdown voltage is. So the first thing we want to do is figure out the capacitance. So I'm going to use this to figure out our base capacitance, and then modify that with our dielectric constant. So our base capacitance is E naught A over D. So again, that's 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared, times our area 0.4 millimeters times 0.3 meters. So those are just meters. divide by the thickness of 0.3 times 10 to the negative 3 meters, because that's millimeters. And that gives us a value of a base capacitance of 3.54 times 10 to the negative 8th farads. And so my full capacitance is modified by my dielectric constant. So the capacitance with the wax paper in is 2.5 times higher. And that gives me a capacitance of 8.85 times 10 to the negative 8th farads. And then what's the maximum potential difference I can put across this? And so the maximum potential is equal to E D. Often this has a negative sign in it because the voltage has, the change in voltage has the opposite sign as our change in electric field, because the electric field goes that way, and our change in voltage goes that way. So like most of physics, it just gives us the direction. So we get negative 3.6 times 10 to the 7th volts per meter times 0.03 millimeters time, we're going to convert the millimeters to meters, and that gives us negative 1080 volts. So we could hook our wax paper up to 1000 volts and not have it break down. So not likely going to get much more than that. Household voltage is only 112 volts, so your little wax paper and tinfoil capacitor should work, at least temporarily. There's all those values nicely written up. And now this is your challenge, is thinking about how this dielectric affects things. The capacitor is connected to the terminals of a battery as shown in the figure. So this is a battery. We'll get into that next. And this is our capacitor. We're going to talk about what these symbols mean next time. But basically we have a capacitor that we're going to insert a dielectric in while still connected to the battery. We want to look at the capacitance, the potential difference, so C delta V, charge is Q, and the electric field between the plates and how those are affected when we insert the dielectric. So pause this and figure out if these increase, decrease, or remain the same. Okay, so hopefully you've thought about that. Whenever we're trying to think about these types of problems, we want to first figure out what remains the same, and the voltage needs to remain the same because voltages of a battery are generally the same until the thing's pretty close to dying. So that means the potential difference across delta V needs to be the same because of the battery. Then we can look at how the other things are affected because of that. We know that C is equal to K times C naught. We didn't change the area or the distance, but we did change this. So these are the same, but C increases. So since K increases, then C increases. Then the charge on the capacitor. I'm going to look at our capacitor equation. Q is equal to C delta V. So delta V is the same, but C increases. So this is the same. C increases, then Q must also increase. And we can use our delta V is equal to ED equation. D is the same. We didn't change any of the physical characteristics. Delta V we said is the same, so delta E must remain the same. So this is the same, this increases, and this stays the same. So none of them decrease. So when you figure out these types of problems, and on your homework you have one where we've disconnected the capacitor from the battery. If you disconnect it, then if it's disconnected, then Q would remain the same. And then go through and figure out what else must change. And here are those answers all nicely written out.